Hey Tutorinos, it's Tutor Pat with a riveting discussion of similar triangles. Let's go. Similar triangles show up routinely in the SAT and ACT, and they give students a lot of grief, and it's completely avoidable. So the first part of working with similar triangles is recognizing that you're working with similar triangles. So let's get a definition. A similar triangle is a pair of triangles that have the same shape, but not necessarily the same size. If I wanted to be slightly more precise about this definition, I could say that the angles inside, the corresponding angles, they're all going to be congruent. They're going to be the same. But the sides, the corresponding sides, the pairs of sides, are in the same ratio. They're proportional. So if we sketched up, notice here that A is opposite the X here. That's going to be in the same proportional relationship as P, which is opposite the X here. So I could write A over P is going to be equal to B, which is opposite the Y, over Q, which is opposite the Y in the smaller one, which is going to be the same deal as C over, which is opposite Z here, over R, which is opposite Z in the corresponding triangle. Notice I keep all my bigs on top and I keep all my littles on the bottom. So it's very important that we keep consistent. Whatever one you decide, if you're going to put the big in the numerator, it always has to be in the numerator. If you're going to put the little in the denominator, it always has to be in the denominator. That's just a good rule of thumb when we're building proportions. We can't stagger it. It always has to be consistent. So bigs on top, littles on the bottom, or littles on top and bigs on the bottom, doesn't matter as long as we're consistent across the proportion. All right. So super simply, a similar triangle, a pair of similar triangles, are triangles that have congruent angles and proportional sides. So these angles are the same, and the sides are in proportion. Beautiful, super simple. Why does it give students grief? Well, sometimes it's difficult to know that the two triangles you're looking at are one, triangles, and two, similar to each other. So we can use some tools from geometry to remind ourselves that we're actually looking at similar triangles. First and these are just taken from our old geometry proofs, is if two corresponding angles are congruent, I know they're similar. Let's talk about why. So if I'm looking at this guy here, and I notice that X and Y, that's the same thing as X and Y over here. Well, that means we do the math, right? It all has to equal 180. That means that this guy here has to be equal to that guy. And if all the interior angles are congruent, I got similar triangles. So if two corresponding angles are congruent, I got myself some similar triangles. Similarly, side, 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 if three corresponding sides are all in the same ratio, if corresponding sides, and corresponding just means the side opposite the shared angle, right? So C would be a corresponding side with R because they're both opposite the Z angle. So if corresponding sides are in the same ratio, I know we're looking at similar triangles. Real quick sketch of that. If I have the old fan favorite, the 3, 4, 5, and then I'm looking at a 6, 8, 10, I notice, oh, hey, these are in proportion. There's a common factor of 2, right? That's being multiplied on the smaller one to get the bigger one. Those must be similar. And then finally, I can use side angle side. which if I have the ratio of two pairs of corresponding sides. So I know that I have two corresponding sides. I know they're in ratio or in proportion, and they're equal. That means just the ratio of two pairs of corresponding sides are equal means they are in proportion. So the ratio of two pairs of corresponding sides are equal, and their included angles are equal. So if I'm looking, I say, oh, I know that A is proportional to P and B is proportional to Q. Oh, and these interior angles that they're sharing are also equal. Well, I think I'm looking at similar triangles. So this is what they are. This down here is how you identify them. Now let's use all that information in concert to solve this problem. And this problem, very crudely sketched out here, is a very common, this is missing here, we need that information to solve it, is a very common SAT, ACT problem. And it'll give you this shape, and it'll say if CD is parallel to AE, what is CB? So CB is this here, right? And many students don't even realize, one, they're looking at triangles, despite me saying most shapes are really triangles. And they fixate on this. Well, this is telling us something very clearly. And one of the big mantra here at Mighty Prep is if we have parallel lines, we always extend and pretend, right? Extend and pretend. I'm just going to put this on airplane so we're not interrupted. Extend and pretend, meaning I'm going to extend these parallel lines here, okay? And I'm going to pretend there's only one transversal at a time. Transversal is a line that transverses or cuts through. So I'm just going to pretend that line is the only one in the world. I'll make it nice and big so it's obvious what I'm doing. And then I'm just going to mark off all my congruent angles. So I know that this guy, for example, has to equal this guy, which has to equal this guy, which has to equal that guy. Then I'm going to pretend that this guy is my only transversal, and I'm going to mark off my congruent angles. I'm going to say, oh, this guy here has to be congruent with that guy, which has to be congruent with this guy, which has to be congruent with that one. Remember, when I have a transversal going through two parallel lines, my little angles are going to be equal, and my big angles are going to be equal. And then, just to kind of top this off, I notice I have what's called a vertical angle, meaning that this angle here has to be equal to this angle here because they're opposite each other. Well, already, we know we have two triangles, and we know that we have totally congruent angles, right? This angle equals this angle, that angle equals this angle, and these are the same two, so they must be similar. So what I'm going to do is I'm going to break them apart and set them equal to each other, making sure that my sides are all in agreement. So here's my baby. Here's my papa, so to speak. I'm going to make sure that the top angle on both, my apex angle is that orange angle, okay? And then this is going to be my red angle down here, and then this is going to be my black angle. Now I notice on my big one, opposite the red is 8, so I'll say opposite the red is 8. And I notice that opposite the black is 10, so I'll make opposite the black 10. And I know on my little one, opposite the black is 5. Opposite, here's the black, right? And here's the 5. Well, immediately doing that, I notice that this is to this. Opposite, same shared, opposite the black angle, opposite congruent angle, it goes from 5 to 10. So I know that, setting that at 5 to 10, it's going to go from x to 8. Right? And I can cross multiply that, get 40 equals 10x, x equals 4. Or I can just say, well, this is multiplied by 2, so this is going to be multiplied by 2. And again, that's orange here to the black angle, and indeed what we want is the orange to the black angle. So I can say, I know, that's 4. And that is how we use similar triangles to solve what looks like a very complicated geometry problem, but is in fact relatively simple. And you're going to see a reliance on special triangle or on similar triangles throughout the ACT and SAT. You see it again and again and again. They are relying on similar triangles and your ability to recognize them as similar in order to solve that particular problem.